All right, we're going to do the video analysis for the lab here. So I'll show one of the videos and you'll repeat the process for the second video. And I'll probably do a little bit of the evaluation of data here as well. Kind of talk about the lab sheet, which I don't have in front of me, but I can pull up on the computer. So over the topics, projectile motion, the lab videos are linked here. We'll use the videos from the Lasallians. All right, so the angled launch video here will be the one I want to right click. I'll do one at a time. Download. All right, they're not too big, these videos, pretty short. It's an MP4. All right, then we'll go over here. Let me just get out the lab sheet while we're at it here. Take a look at that. So force diagram of the ball I went through in the last video I had made. You can take a look at that. Sketch the approximate graphs of the ball's kinematic curves. Do not plot points. Sketch what you think the acceleration versus time graph should look like for each direction. So this is once you do the video analysis, we'll sketch these in. Maybe these should be a little bit bigger, you know. But we're just very rough sketches. All right, so you open up Logger Pro. So if you're at home trying to do this, you can get it done pretty quickly. I put on the daily schedule that I wanted you to try to do it, right? So, you know, again, I can't remember if you all have Logger Pro at home or not. It's too hard to keep track of that. So try to perform video analysis. If you can't, look at the graph here and try to go through it. Maybe here at school we'll just do the second one. I'll give you the graphs for this one, and then you can do the second one. All right. So Logger Pro. First step is always insert movie. All right, it's in my downloads, so that's going to be, I have to navigate to that. Let's see, downloads, angled launch, open. All right, we took a little trip over the Callahan gym, moved one desk, did our video, and then sanitized that desk. All right, so students sitting in the chair here. We have 4 meter sticks across the ground. If you play it in Logger Pro, it's going to be real slow. It's probably going to be even slower because of my castifying right now. It looks all choppy. That's okay. It doesn't matter. Each frame is there. I think I shot this. Uh-oh, I better. No, never mind. I'm not going to take that call. I think it's. The phone's ringing here, and I'm always worried it's about the kids, but I don't think this one is. 30 is familiar to me. All right, so we want to find the frame where it just leaves Tyler's hands here. All right, so he's getting ready to throw it. Getting ready to throw it, still in his hand. All right, I'm going to click the little arrows here. If it starts ringing immediately again, I know who it is. All right, there it goes. It's left his hand. This is going to be our first frame. Now, the tricky thing here is that it's going to the left, right? I should have had him throwing it to the right. I don't know why we didn't do this the other way. So pull up this menu here. All right, first thing we're going to do is set our coordinate system. That's the third button down. We make the middle of the bowling ball. Now I'm going to grab this dot right here and flip it over. Whatever side that dot is on, that's the positive x-axis. All right, that's the positive x-axis. So there it goes, positive x-axis. All right, and then I'm going to set my scale here. That's this 4th button down. I'm going to drag that across my meter sticks. All right, and that's 4 meters. Now, I'm hoping this is going to be a very nice, precise video. Options, movie options. Allow, or first VA point defines movie times 0. Advance the frame after adding a new point. Maybe we'll do 2 frames rather than 1. Get this done a little bit quicker. I'm going to click the center of the ball as it's flying through the air. Now, that gets a little bit hard to see, right? I am going to plot this until just before it hits the ground. Now, as it's moving faster, you'll see you'll see it, the points get farther apart, right? So it's moving faster as it comes back down. It's gaining energy. All right, just before it hits the ground, and that's after, so I'm not going to add a point there. All right, then you go page, auto arrange, makes everything nice. I'm going to make the video a little bit smaller and hit page auto arrange again. We have X position versus time and Y position versus time. Oh, when I flip the axis, that's the other problem. The Y position versus time, it's not right now. It's making down positive. Oh boy, okay. I'm gonna go back here. I'm gonna rotate this back in the other way. Wonder if there's a way to flip Y. This is a pain. I'm gonna leave it like that. I'm gonna leave it like that, the original way it was. So the X velocity looks negative. All right. So X position versus time, Y velocity, Y position versus time. So X is nice and linear. Look at that. That's cool, right? I can put a fit line on the X direction here. And look at that correlation, almost to 1. So this thing moves in the X direction at a constant velocity. That's what that means. Constant velocity of about 4.392 meters per second. The Y direction, this is curved. So remember, a curved position versus time graph means there's acceleration involved here. So this is really interesting, right? In the X direction, there's no acceleration. In the Y direction, we do have acceleration. That agrees with what we said. Now, if you remember what that acceleration should be, all right, the acceleration should be negative 9.8 meters per second squared, all right? So what I'm going to do here is I'm going to insert another graph. Insert graph. Ooh, the velocity versus time, all right? It automatically makes it just the Y. So if you right-click and you go to graph options, you can change that to be X velocity and Y velocity. All right, we'll do a page auto arrange. So now we have position versus time is the blue position versus time, that's the Y. There's actually a way to put a curve on this, a curve fit. It's the F of X, curve fit. We're going to do it for the Y velocity. And you got to pick what you think, oh, sorry, not the Y velocity. You want to do it for, I'm in the wrong graph, that's why. Hold on a second. Click that graph, do Y video analysis. You got to pick what you think it looks like, and that looks like a quadratic to me. Then you hit try fit, and there you go. And look, AT squared plus BT plus C. All right. So if you know, remember El Grande, delta X equals 1/2 AT squared plus V initial T. The initial Y velocity is B. The acceleration is twice whatever A is. So that number actually came out really pretty good, and we'll see why in a second here. All right, let's take a look at the velocity versus time graphs now. So this is a curved position versus time graph, so that must be a linear velocity versus time graph. So the blue line is a linear velocity versus time. So blue represents the motion in the y coordinate system, the y-axis, parallel to the y-axis. The red represents the horizontal motion, the x motion. So in the x direction, it's nice constant velocity. See, it's about 4.3 meters per second the whole time. I don't even need to put a fit line on that. But let's take a look at this y velocity here, right? We do r equals on the y velocity, hit OK. We put a fit line on there. Check it out. The slope of that fit line is about negative 9.1. All right, so the acceleration in the y direction is about negative 9. The curve fit up top of it is actually better, right? Because if this follows El Grande, y equals 1/2 delta y equals 1/2 a by t squared plus v initial t, right? El Grande, the term that's showing up here capital A in our curve fit box is 4.764. All right. So if I double that, it's going to tell me what the acceleration is. 4.764 times 2 is about 9.5. So there's a discrepancy between these two graphs. It's hard to say what that is. It could be this last data point. If I kind of shrink this down a little bit to the middle portion of the graph, we might get a better data set, right? So 9.5, that's a little bit better right there if we only look at part of the motion, right? Why that is, I don't know exactly but this is a better correlation too. It's almost 1.0. It's about negative 9.5 is the acceleration in the y direction, and acceleration due to gravity, remember, is negative 9.8. So why is it a little bit different? Well, you can see in the ball in the video here, all right, it didn't land exactly even with the rulers, right? It's a little bit farther behind the rulers. So what that means is that the distances we measured here are actually probably a little bit longer than they appear. The scale, right? If I move these meter sticks back, there's like a trapezoid happening here, right? Like if I set the scale to be more relative to where the ball is, it probably would be something more like that. All right, and you'll see what happens is that shifts all the data. Look at that, just that little bit of difference in shifting the scale here makes it a lot more accurate. So, maybe we should have taken some more time and gotten this ball to go more straight over the rulers. It's difficult. So just a little bit off path, right? That drastically changes the way you set the scale. It's very tricky, right? So now you got to imagine like a perspective drawing, right? Look how this is a straight line on the floor. Look how steep that goes back, right? So if I adjust my scale to where the plane the ball is actually moving in, I actually get much better data. I actually get much more accurate data. So you could go with that as well. The main takeaway here, okay? The big takeaway is that the acceleration horizontally is just 0. When he throws this ball is moving forward at the speed he threw it. It doesn't change. 4.3 meters per second. It's the velocity he's moving forward with. That's the speed with which he threw it forward. But in the y direction, we have gravity acting. So the ball goes up and it gets pulled back down. And the y velocity is changing by negative 9.8 meters per second each second. So on the way up, it slows down, it loses speed. But on the way back down, it speeds up, gaining that speed back due to gravity, all right? So gravity takes away the velocity as soon as it starts leaving his hand. But then once the ball gets to the peak over here, gravity is pulling it back towards the ground, accelerating. So the mathematics of solving these problems is pretty nice. You look at the setup, all right? You say, okay, it was launched at a certain speed, at a certain angle. Let's figure out how it was launched initially in the x direction and initially in the y direction, right? And then once you do that, you can say, okay, in the x direction, I know it's just going to keep moving that speed, right? So it's in the air for 10 seconds. If this ball was in the air for 10 seconds, it would move forward 4.3 meters while falling down, all right? So it's pretty interesting. The projectile motion, this curved projectile motion, it's a combination of horizontal and vertical motion. Horizontal, for instance, if you were to track the shadow of this ball on the ground, it would just move at a constant speed. If you were to track the shadow of this ball on a vertical plane, it would go up, come back down. Actually, it would start in the middle, go up a little bit, and then come back down and hit the bottom, all right, in the vertical direction. So that's the essence of two-dimensional motion or projectile motion, that each direction you treat independently of one another. They do share one variable with each other, and that's time, right? So however far it's moving forward, however long it's moving for, it's moving that length of time in both directions. So you'll see how the kinematics plays out once we get going. So let's just quick run and look at the handout really quick. So position versus time graphs, right? Can I mark on here? I guess it won't stay very long. But position versus time in the x direction is just, oops, actually it was, actually went down like that, right? Velocity in the x direction was constant and negative. Acceleration would have to be 0 the whole time. In the y direction, we saw something a little different, right? It kind of went up or down, right? The y velocity, um, let's just going to go back to the Logger Pro and double check that real quick. Yeah, look, zeros right there, right? So we got to be a little bit careful in doing that one. It kind of starts at a positive y velocity. Once it gets to the peak, it has no y velocity, and then it gets negative y velocity. Acceleration, though, the slope of that line is negative 9.8 the whole time. Describe the motion of the ball, you can do that. I don't even know what I'm drawing on here. Am I drawing the PDF or am I drawing on the screen? I guess it's a tool. Anyway, I don't know. Those will go away, maybe. Know what those are, how to get rid of those. All right, describe the motion of the ball in each direction. Use graphs to help you, or imagine the shadow of the ball on the floor. So I just talked through this. Rewind. I gave you that answer already. From your graphs, determine the x acceleration, the y acceleration of the ball. I already told you that. Go back, fill that out. The horizontal ball, complete video analysis. So we'll do that in class. All right. We'll do the horizontal ball launching class, I suppose. This is for the first half of the alphabet. And I'll print out this for you guys, this other graph. You can just take it. All right. All right. Cool. I think that's about it for this video. Talk to you guys later.